We want to do some examples of the chain rule. Now, the chain rule basically is designed to take the derivative of a composition of functions, which is actually what we're going to do most of the time we take derivatives. So if I have a composition of functions, think of it as working your outside on the way in. So f prime of my argument and then times the derivative of the argument. Now that sounds very vague and abstract, but basically it means that if I have more than just a variable to a power or more than just the sign of a variable going on, that there's probably some deeper layers of derivatives. So let's do a simple example. If I said I want to differentiate x cubed, or I want to differentiate, maybe 6x squared plus 4 cubed. Well, in the first case, this is just variable cubed. This is easy. This is just 3x squared. Think of this as I'm differentiating thing cubed. So it should be 3 times thing squared. But the difference is right now my argument is just the x. I'm cubing the x, so the chain rule factor technically would be the derivative of x, which would be simply 1. But in the second case, my argument is 6x squared plus 4, so my chain rule factor would be the derivative of 6x squared plus 4. And that quantity would be 12x. That means I have an additional factor of 12x, which is called, again, the chain rule factor. So my final answer, my bestest answer, would be this. Had I cubed this to begin with, had a big, ugly polynomial, differentiated that polynomial and factored it, this is what I would have gotten because this would have shown up in my final answer. But the chain rule is very simple to apply. If my argument is more than just a variable, then the derivative of my argument is not going to be 1. If my argument is just a simple variable, the x, then the chain rule factor is 1. It's not necessary to write times 1. So now let's do a few examples. Okay. So I want to find the derivative, let's say, of 8x cubed minus 6x squared plus 7, and that's raised to the 4th power. Okay, now I'm differentiating a function raised to the 4th power, so I actually have to put parentheses around the whole quantity because this being an operator says it's going to differentiate everything that follows, including the exponent. Strangely enough, if I leave the outer parentheses out and I was using a graphing calculator or a computer technology, what it would do is differentiate the quantity and then raise the result to the 4th power. That's not what I want. I want to take the derivative of quantity to the 4th power. So that will be, this is thing to the 4th. So the derivative is 4 times thing to the 3rd. Okay, that's the most important part that I got that. But now the chain rule factor is times the derivative of thing. Okay, this doesn't get an exponent. That exponent's already been dealt with. I had thing to the 4th, the derivative 4 thing to the 3rd times derivative of thing. And the derivative of thing is called the chain rule factor. So this would be 4. And this quantity here would be 24x squared minus 12x. Now I'm done with the calculus. Can I give a better representation of this answer? Yes, I can, because I can factor this last quantity. In fact, that quantity right there, I can clearly factor out a 12x, leaving 2x minus 1. So if I factor out that quantity there, and I combine these two here, I'll have 48x times 8x cubed minus 6x squared plus 7 to the 3rd power times 2x minus 1. Now that's the best answer I can give because the calculus is finished and it's in a factored form, which makes it the most useful version. All right, let's try another one. Y equals the square root of the secant function. Now this looks a little bit odd at first because you're not used to seeing trig functions inside of a root particularly, but it really doesn't matter what exponent I use, it's how I represent this. So this is the same as writing the secant of x all raised to the 1/2 power. Now notice I cannot put the 1/2 here. That notation is reserved for positive integer exponents. And I'm certainly not going to put the 1/2 on the x because I'm not taking the square root of x, I'm taking the square root of the entire secant function. So this representation, now I have function raised to a power like we did in the last example. So my derivative is power function to the power -1. And at this point, I need to take the derivative of the secant function itself, and that would be my chain rule factor. So when I do that, I will have 1/2 times this function raised to the -1/2, and then the derivative here would be the secant times the tangent. Now, when you look at that, you notice I have secant function raised to a power, and then I have secant function, which is equivalent to secant function raised to the first power. So the rule here is, of course, I add exponents. So the -1/2 and the +1 give me a +1/2 power, which basically just puts me back to here. Back to square root of secant function, and then times the tangent not being under the root. So there is my final answer. That's the best answer I can give, and it was the simplest answer. All right, let's continue. Back to my rag here. All right, let's take one that's just a little bit more complicated still. So let's consider y equals the square root of 2x minus 3 over 4x plus 5 raised to the 3rd power. Now that just looks downright scary. And of course, I can use quotient rule on this. But remember, if you can rewrite something as a product conveniently, then product rule is always easier to do than quotient rule. So that's not obvious at first, except I can think of this as being a negative exponent. So I can rewrite this as 2x minus 3 to the 1/2 power multiplied 4x plus 5 to the -3rd power. So now I have a product of two functions, each being raised to powers. So I'm going to ultimately have to use the product rule, but within my product rule, I will also have chain rule. So this one here is kind of busy. So let's go slow. dy dx. That's the first times the derivative of the second plus the second times the derivative of the first. And whatever you do, don't lose those exponents, okay? So I haven't lost any of my exponents. Now, when I differentiate this, I'm going to have exponent function exponent minus 1, and then times the derivative of the argument. So that I'm going to have to use the chain rule on that term right there. So this will become 2x minus 3 to the 1/2 times -3 4x plus 5 to the -4th, because I decreased the exponent by 1. And then I'm multiplying by the chain rule factor, which in this case would be times 4. Next term, 4x plus 5 to the -3rd. And then the derivative of this would be 1/2 2x minus 3 to the 1/2 minus 1, or -1/2. And then the chain rule factor would be the derivative of 2x minus 3, which is times 2. Okay. If I walk away right now, my calculus has been flawless. But I am a long way from a finished answer, because clearly I can combine, I can factor, I might even be able to cancel some stuff. But if nothing else, I want my final answer as at least a product or a quotient, not as a sum. So look for the GCF. Now, when writing the GCF, I know I'm going to get a 2x minus 3 in both terms. I know I'm going to get a 4x plus 5, in both terms. So when you're selecting the GCF, you always choose the smaller of the two exponents. But one of the nice things you notice is the exponents differ by exactly 1. These exponents differ by exactly 1. So when I pull out the greatest common factor, that will leave me one whole term, not another exponent, just the factor itself. So my common factor here will be 2x minus 3 and 4x plus 5, but to what powers? Positive 1/2, negative 1/2. So negative 1/2 is the common factor. Negative 4, negative 3. So negative 4 is the common factor. Now, what does that leave me with? Well, coefficient-wise, there's a negative 12. I used up all of that, and these differ by exactly 1. So there's exactly one factor of 2x minus 3. And before you go any further, you can always distribute. When I multiply this one by this one, I would add the exponents, negative 1/2 and positive 1. That gets me back to here. I pulled out the whole factor. Great. Now, plus. Coefficients, 1/2 times 2, that's a 1. I pulled out the entire factor here, but I pulled out one more than I have here, so there would be an entire factor of 4x plus 5. Again, 4x plus 5 to the first power times 4x plus 5 to the negative fourth power. That gives me my 4x plus 5 to the negative third power. The 1/2 times the 2 canceled, and that guy factored out. So now this is looking kind of pretty. All I have to do now is kind of finish this off. So let's distribute here. That would be negative 24x plus 36. So if I put all of this together, it looks like I have negative 24x plus 4x, that's negative 20x. I have positive 36 plus 5, that'd be plus 41. So what I have now is a beautifully factored answer with lots of negative exponents. So what do I do with that? Well, this is where I now simplify by putting the negative exponents back in the denominator. Had I done the original problem as a quotient rule, I could have done it, but it would have been very difficult algebraically. But now I have something that's really simple to work with. There's my numerator. And my denominator will be square root. And this will be 4x plus 5 to the positive fourth. So if you go back and look at the original problem, I had a quotient that had a 1/2, that had a 3. But if I wrote it as a product, I had these exponents. You notice in my final answer, this exponent decreased by 1, this exponent decreased by 1, and that's exactly what I should have expected. So this one here was difficult. This was more complicated than most, but this is the kind of problem, if you can do this one, then you can do anything.